Assalamu alaikum guys. Is now we are moving to lecture 5 in week 3. It is about the branching ratio and the partial half-lives. So what is branching ratios, why we need them? Some radioactive materials have more than one decay simultaneously, means they have in one sample you have more than one decay at the same time. For such materials, we use branching ratios for each decay process, which actually gives us the probability of each decay process. These decay probabilities are called branching ratios. So, branching ratios in particle physics or nuclear physics, the branching ratio, or sometimes called branching fraction, for every decay, or is the fraction of particles which decay by an individual decay mode with respect to total number of particles which decay. Because at any time in such samples more than one decay process is going on, and we want to find their probabilities of decaying. It is equal to the ratio of the partial decay constant to the overall decay constant. So overall decay constant is different from the partial decay constant. So we have overall partial half-life, and we have also partial half-lives for uh, each decay mode in these kinds of samples. So we specify the relative intensity of competing modes such as alpha, beta and gamma in the samples by branching ratios. Actinium is an example in which we have three kinds of, actually the two kinds of beta decays, and here we can show you, we can divide this in three separate processes. Alpha emission, which has 0.006% of occurrence of our branching ratio. Beta minus emission has 83% chance of occurring. Beta plus and electron capture together have a chance of 17%. So actinium is an example in which we have more than one decay process, and we have to find the partial decay constants for such sample. And in this lecture we will find how we can calculate the partial half-lives and partial decay constant for this sample. Its total half-life is 29 hours. So total decay constant can be calculated by using the formula of half-life, as which was calculated in the last lecture, which is equal to natural log of 2 over half is equal to lambda for total decay constants. And if we put the value of half-life, we will get the total decay constant equals to 6.6 into 10 to the power minus 6 per second. Total decay constant is composed of partial decay constants. For example, for this example, lambda alpha, which is the partial decay constant for the alpha decay, and lambda beta minus, which is the partial decay constant for the beta minus mode, and lambda beta plus and eta, which is the partial decay constant for beta plus and electron capture. So we can find the partial decay constants for this sample very easily just by multiplying the total decay constants with the occurrence probability of occurrence, such as we can find the lambda alpha by multiplying total decay constant lambda t with the 0.006%, and the percentage is converted into the number by multiplying it to 10 to power minus 2 or divided by 100, and this after putting the value of lambda t, total decay constant, we can find out, and you can do it by yourself. And similarly for the partial decay constant for negative beta decay can be calculated by multiplying the total decay constant with the its occurrence probability 83%, and after substitution of lambda t you can find the partial decay constant for the beta minus, and similarly the partial decay constant for beta plus and eta can be calculated by multiplying lambda t with its occurrence probability, and you can do it by yourself. It's very easy. So after this we can find out the partial half-lives of alpha, beta minus, beta plus, eta in the actinium sample by using the formulas as shown on the screen. So the partial half-life for the alpha decay mode can be calculated by this formula. The half of alpha is equal to 0.693, which is the natural log of 2 divided by partial decay constant. By putting the value of partial decay constant for the alpha decay, you can find the partial half-life of the alpha decay mode. Similarly, you can do for the beta minus decay, and you have to put the value of partial decay constant of beta minus decay, and you can find out the partial half-life for this mode. And similarly, the partial half-life of beta plus eta electron capture can be calculated in a similar way. So here I am showing you decay possibilities of actinium 226. 226 is the A number, 89 is the Z number. So it has different possibilities to decay, such as on the right hand side it can decay into TH thallium with minus beta minus decay, negative beta decay, with the occurrence of branching ratio of 83%, and with that it can also decay directly to FR by the alpha decay with very less branching ratio probability, and it can decay to R, and it can further decay to Rn with the alpha decay. So the aim of showing this graph is to just to understand the partial decay mechanism in one sample, and this is an example of element of actinium. So these some isotopes have some partial decays, and here I have put some examples, just like copper 64. It has also more than one decays, arsenic 74, and there are different materials. So you can see in the slide, copper 64 has a half-life of 12.70 plus minus 0.002 hours and decays by this by positron emission to nickel, and then it has also probability of 39% branching ratio decay, beta decay to zinc, and also 43% by electron capture to nickel, and 0.475% gamma decay probability. So here is the example of cesium 132. It can decay into two modes simultaneously, beta minus and beta plus. Beta plus has 98.2% 1.3% branching ratio. It's more chance to decay via beta plus, and only 1.87% beta minus decay chance. So these kinds of samples in which we have more than one decays, it is possible to find out the partial decay constant and partial half-lives for these kind of elements, isotopes. So I think it will be helpful for you to understand, and I recommend you to read your book for detailed discussion. Thank you.